Okay, let's go for the next experiment. It's gonna be Young's double slit experiment. This experiment is very important, very famous. Why? Because this experiment proves that light behaves as a wave. At the beginning, it was believed, according to Isaac Newton, that light behaves as a particle. Now, with this experiment, it was shown also that light behaves as a wave. That's why it's very important. Okay, so in this case, we have a double slit, correct? We have a screen, and we may pass laser through this slit, right? In this case, we have the distance from the slit to the screen, 5 meters, actually 5 meters, not centimeters, 5 meters, correct? And the pattern that is found is like this, right? So this is the pattern that is found using waves. So light behaves as a wave. Okay, at the center we have constructive interference, very bright, right? And then we have destructive, constructive, destructive, constructive, right? We're paying attention only on the bright fringes, constructive interference. Okay, at the center we have m equals 1, that's m stands for the order number, right? Then the second, or the first bright fringe is gonna be m equals, at the center we have m equals 0, one more time, m equals 0. Okay, later we have m equals 1, m equals 2, and so on, going above or below, right, the center one. Correct. Now the equation that is used for or is found for this diffraction double slit interference is gonna be d sine theta equals to m lambda. Lambda is the wavelength. Correct. D is the distance between the two slits. But because the angle that is used for each bright fringe is small, according to this figure, correct? We use the prox of sine theta, prox about tangent theta. When we use that, well, we create a triangle, right? Triangle. This is opposite over adjacent, and tangent is opposite over adjacent, right? So the equation becomes dy over L equals to m lambda. Okay, now we have three cases in this experiment. We have d1, right, the distance between two slits equals to 0.25 millimeters, d2 0.50 millimeters, and d3 0.75 millimeters. Okay, for case 1, let's do two parts, part A and part B. Part A, let's say m equals 1, or in part B, m equals 2. Okay, for example, we are right here, m equals 1, we're looking for y1, that's giving the experiment, correct? So imagine this is the case, this is the pattern that you will see in the experiment. We have at the center very bright fringe, and then we have more fringes to the right and to the left. From the center, let's measure the distance from the center of the brightest spot to the center of the second one, or the first one in this case, right, which is labeled m equals 1, right? It's gonna be, this is gonna be y1. You can measure it in the experiment, correct? So taking that value, of course, it's gonna be millimeters. Later you have to convert it to meters and find the experimental value. In this case, we have the theoretical value from lambda is 5,032 nanometers. It's gonna be the theoretical value. So from the experiment, right, let's start from the equation from here. Let's start from lambda, gonna be dy over ml, correct? L is given one more time is 5 meters. Great. Now, once we get again the distance from the center branch to the next one, we label m equals 1. Well, we plug the values in the equation. Remember, m is equal to 1 for this case, and find the experimental value. Then let's use the percent error to find the percentage, right? What is our percent error for this trial? Let's go for part 2. Part B, m equals to 2. Again, m goes right here, right? That's gonna be 2, the value for m. And the same thing, let's find y2, correct? The distance from the center to the second right fringe, right at the center, as you can see from here, it's gonna be y2. Okay, let's give it in millimeters. Later you have to convert it to meters and find the experimental value using this formula one more time. Now again, n is equals to 2 for part B, correct? In meters, and find the percent error. Right, the percent error, as you know, is represented in this way. Usually, right, percent error is equals to lambda theoretical minus lambda experimental minus divided by lambda theoretical times 100%. Correct. That's the formula for percent error. Let's go to part 2, right? Case 2, right? D2 equals 2.50 millimeters. The same thing. Let's go for m equals 1. Find y1, write that distance in meters, right? Find the experimental value, okay, for the wavelength using that equation, and then find the percent error. Let's go to part B. M equals 2, and now 2 goes right here, right? Perfect. Let's find the new distance from the center to the center of these branches, by fringes, correct? And right here, right? Find the percent, find the experimental value, and find the percent error, right? Perfect. Now finally, let's go to the last case. By the last case, the fringes are very, very close. It's hard to tell what the distance between two fringes, correct? To do a good approximation, right, let's do it this way. Instead of taking, right, m equals 1, right, like in this picture, in the formula, okay, let's make m equals 1, but instead of doing it this way, let's take a set of right fringes, right? Let's say n equals 6, n equals 7, n equals 10, right? And find the distance for all of them, for that set. Imagine, like in this case, is 6. Okay, this is 6. And imagine that the distance is, let's say, 1 centimeter. Correct? Now we're looking for, because we're dealing with m equals 1, we're dealing with the distance between two fringes, bright fringes. Correct? So then we divide that by the numbers, the distance by the numbers of fringes to find, right, the distance between two fringes. It's like at the average. We're looking for the average, right? So let's do it that way. So y now is equals to d over n in millimeters, right? And then using y, the value for y in the same formula, correct? We get the experimental lambda. And then finally, let's go for the percent error. So in this way, we are dealing with these 3 cases. The special one is going to be the last one, because again, the fringes are very close, but we use that technique. Also, we can use the same technique right here, right? Right here and right here. The answer must be the same, right? Because the distance between them is the same. The distance is the same. So it's the same as half, right, one distance or half the average. The average is going to be the same thing, correct? The same distance between two bright fringes. Okay, let's go to the experiment to find the y, right, the distance, y1, y2, right, y1, y2, and to find, right, this distance and the numbers of fringes that you want to use. It's up to you. You can use 6, 7, 10, it's up to you. Okay, let's do it. Okay, this is case 1. Now it's case 2. Finally, case 3. Okay, we have the 3 cases. Please do the measurements and see you in the next experiment. Bye.